Hi, welcome to the Kinetics and Equilibrium unit. We are going to get started today with collision theory. And the question of the day is, how can you get a chemical reaction to progress faster? Collision theory describes what needs to happen for a chemical reaction to actually happen. And really what we have decided is that our particles must come in contact, they have to collide, and they have to collide with enough energy in order to break bonds and form new ones, and they have to hit at just the right angle or the proper orientation. I like to call that the chemistry home run. If you think of a home run in baseball, in order for the batter to hit a home run, the bat has to hit the ball, they have to collide. And that ball has to be hit with enough force to hit the ball really far, and it has to be hit at the right angle so that it stays in the field. So in case you don't know, the batter's going to stand here, and the goal is to not let the ball go outside of the diamond. So you want to hit it really far and not at a weird angle so it flies out into all of the people sitting on the sides watching, but instead goes far out into the outfield. Here's kind of a picture of what we mean when we talk about correct orientation, hitting at the right angle. So if you see we have this diatomic bluey purple molecule with the diatomic green, this is going to be a correct orientation because here we can get the blues to break apart and the greens to break apart because they've matched up with the opposite color. Where over here, you'll have a green and a purple, but this other green is kind of left on its own, and this purpley blue is kind of left on its own. So in this case, we would only get one of these molecules, and these atoms existing by themselves is too high of an energy state for that to really happen. So the molecule, the two molecules won't react if they don't hit at the right angle, but hitting side by side, they're going to have a better time with that reaction because both of the atoms of the molecule are able to react at once. And molecules really like to exist in a low energy state. So this is going to be a green light. We're going to do this one, but over here with these lone atoms, that's a very high energy state. It's not going to want to do that. So this is what we mean by the effective collision. Collision theory explains to us how we can get effective collisions to happen, and there are a few ways. So number one is that we have to consider the nature of the reactants. Some chemicals just don't react with other chemicals. If you think of oxygen, oxygen will oxidize a lot of stuff, but this pencil made of plastic, carbon, will not react with oxygen. Meanwhile, lots of metals are oxidized by oxygen. So if you think of the noble gases don't like to react with anybody. We can get them to react in a lab under like really specific conditions of temperature and pressure. Usually they're pretty wild conditions also. They don't really happen in nature. I mean, sometimes yes, but not really. If you remember the noble gases, they have that full valence shell, so they don't really want to react. Meanwhile, the halogens are just one electron away from a full valence shell. And the lithium's group 1, they're only one electron away from a full valence shell, so they want to like really get to reacting. So what chemical reacts with what is going to actually be a really big role in whether they have a reaction or not. Typically, when we increase the temperature, the rate of the reaction will also increase, and that's because more particles are going to have effective energy in order to actually have a reaction. For chemistry, typically this is true. Higher temperatures means a faster reaction. In biology and some biological systems, sometimes you can actually break or denature proteins when the temperature is too high. So in an overall chemical reactions context, not necessarily true, but for your like really just chemistry, not really any biology in their reactions, it will be true. I just want you to know this in case you're a biology kid going forward. Sometimes in biology, the temperature can break reactions, but for pure chemistry purposes, a higher temperature typically will have more particles with more energy to have better reactions. If we increase the concentration of our chemicals, typically we're going to have better reactions, faster reactions, and that's because we have more particles. I mean, if you were in a crowded room, you are more likely to bump shoulders with people. That is certainly something to consider when we're talking about how to get particles to react. Obviously, the more there are, the more likely they are to hit opposing particles in order to have that chemical reaction. This one you may not have realized, but if you increase the surface area for solids, you are going to have more of your particles available to react more quickly. So here we have sugar is just a really good example of this. If you have regular granulated sugar like you would use to bake a cake, all of those little tiny sugar crystals obviously are made of tiny molecules. But because that sugar crystal is so small, you have a very large surface area of sugar there. So there's not a lot of shielding from other molecules, so that if you wanted the sugar to react with something, a lot of the sugar molecules are in contact. On the other hand, if you have sugar cubes, the sugar cubes are like 2.5 grams of sugar, and they're pretty big. So what happens is only the sugar molecules on the very outside of the cube are able to react. And once they do, they kind of fall off, whatever. Now there's a new layer. So it kind of goes layer by layer by layer. So this is going to be a much slower reaction than the granulated. A lot of the times when you get asked this question, it is considered for metals. So you may not know, but when you buy metals from a chemical company, they're typically going to come in like a plastic jar. Sometimes they're little nuggets. Sometimes they're like beads. They're shaped nicely. Other times they're grains or dust even. So the grains and the dust are smaller particles, which means they have a larger surface area. And then like the chunks, the strips, the sheets, you have to kind of consider the shape of these things. The bigger the chunk of metal, the slower it's going to react versus the same amount of stuff, but in tiny little pieces. This one is only true for gas systems, and that is to increase the pressure. It would also be the same as decreasing the volume. So you get these gas particles very close together, and they are more so going to be able to react with each other. This is true if you've ever smelled anything stinky. If something is stinky, let's say in like a big auditorium, and you're all the way on the other side of the room, then maybe you won't smell the stinky smell. But if you have you and the stinky smell in a small closet or a small room, you've shrunk the volume, you're going to smell this stinky smell. So this is true whether it's a stinky smell or a chemical reaction. The closer your particles are to each other, the more likely they are to react. So in the case of gases, that's going to be an increased pressure or a decreased volume. Those are the same result. If your gas is dissolved in a liquid, this is also true because the gas is going to be squished down into the liquid and it doesn't really have the opportunity to evaporate out of that solution. Last up is the introduction of a catalyst. If you have taken a biology course, a catalyst and an enzyme are pretty much the same thing. Enzymes are just the term that we use for biological catalysts, and then a catalyst is just like a general term. Catalyst really just provides a shortcut for your chemical reaction. So this squiggle might be the real path, but the catalyst will take you on the shortest path from point A to point B. A lot of the time what happens is that your catalyst is going to like grab on to molecules so that you kind of have a place for molecules to react. It's typically going to carry molecules from one place to another. Usually they are going to speed up your reactions, and they also are going to decrease the amount of energy required for the reaction to happen because it has this assistant there to kind of help things out. So let's say, for example, and we'll talk more about it in the next video, or rather the next lesson. Let's say that it takes 10 kilojoules of energy for your reaction to actually happen. That's called activation energy. With a catalyst helping, the activation energy may decrease to 8 kilojoules. And now your particles only need 8 kilojoules of energy to actually have a reaction as opposed to 10. So the catalyst is definitely going to increase the rate of reactions and ensure that there are more effective collisions. That's all I have for you on collision theory. Stay tuned. Make sure to subscribe because there is a video coming that will help to kind of visualize collision theory, and I would love for you to see it. I don't want you to miss it. Please leave any questions you have in the comment section below the video, and I'll see you in the next one. Bye.